2's cancel. You look at this and you say, well, that looks kind of funny. It looks kind of like a Fourier series, doesn't it? It's kind of like a Fourier series. This actually has a fancy name. It's not quite a Fourier series. Because if it were a Fourier series, what would these coefficients be? Would they be f? No, they'd be integrals of f. So the Fourier series has integrals of f here. So note, Fourier series has inner products here. So here I'm just taking samples. So it's like a Fourier series, but it's not quite. This has a name. This thing is called the discrete Fourier transform. And in fact, really when people talk about this thing, this is sort of the more theoreticians thing. This is sort of the infinite version. Usually people only take a finite sum. So they go from n equals 0 to something. That resulting thing is the official discrete Fourier transform. And that's actually what MATLAB computes if you ask for the fast Fourier transform of something. Is it computes this guy, or a finite variant of that. And why do they call it the fast Fourier transform? Because there's a trick to computing it even faster than doing it this way. Turns out computing it this way, directly from this formula, is not the most efficient thing. There's a fair bit of redundancy. In particular, you end up doing a lot of reuse of calculations here. So there's a quick way to organize that, which I don't want to spend time going into here, although if you're interested, I can tell you about it. But basically, this is the sort of machinery that one likes to use. And what I think I'll close with is the final commentary. I won't do this out. There's some homework problems that you have involving the discrete Fourier transform, and involving using the discrete Fourier transform to solve difference equations. Because the idea being, see, what is the Fourier transform very good for? The Fourier transform is good for derivatives. Why? Because if you take a derivative of it, of a Fourier transform of something, so last time that there's integration by parts, comes to your rescue, moves the derivative off the function, puts it on the e, taking derivatives of e things is very easy. Here, the derivatives don't work out necessarily so well, but differences do. Differences work out pretty easily, because again, what happens if I take the sum or difference of these guys? By bumping up, and it means that I end up, if I take a shifting it by an integer number of samples, then what ends up happening is I just shift this n up or down a little bit. So it changes my sum a little bit, it re-indexes my sum, and it makes it possible to manipulate difference equations with relative ease. The resulting thing is that, in fact, if you can solve characteristic equation for differential equations, that's good old polynomials, you can end up with characteristic polynomials for difference equations as well, and they come right out of this discrete Fourier transform. So that's a fabulous place to end. So I hope you guys have a great weekend, and see you next time.
You too.
Yep.